Subscribe our channel, press the bell icon for latest videos.
Hi friends, here in this video we are going to see a problem on shear stresses, that is the second problem, and for that here is the question. So let's get started. The question is, an I-beam 350 mm multiplied by 200 mm has a web thickness of 12.5 mm and a flange thickness of 25 mm. It carries a shearing force of 200 kN at a section. Sketch shear stress distribution across the section. So in the question it is mentioned that here we have an I section, so I'll write the data. There is an I section. The cross section is 350 by 200, so 350 is the total width and 200 mm is the depth of the section. Then web thickness is given 12.5 mm. And flange thickness is 25. It carries a shearing force of 200 kN. Shearing force I'll denote it by F. (200 kN). So it is 200 into 10 raised to 3 Newton. Here we have to sketch the shear stress distribution across the section. That is the shear stress distribution diagram. So this is the question in front of us. Now into the solution part. First I would be drawing the I section, giving it the dimension, and then we'll move further into the problem. So into the solution part. The flange thickness is given as 25 mm and the overall width is 350. So I would be drawing the flange first. This is the origin and here is the web. Now giving the dimensions to it. Since the total height or the total depth is 200, here we have 25 plus 25, that is 50. So the remaining height is 150 mm. Now, after reaching up till here, since we can see here that it is a symmetric I section, for that X bar is the location of the Y axis for this I section. So this is the Y axis and the location is denoted by X bar, which is half of 350, that is 175 mm. Next, since it being a symmetric section, even the X axis would be at half of the total height, which is 200 mm. So here is the neutral axis. Whose distance from the top and bottom are same, because here we have symmetric section. y bar is 100 mm. From top as well as bottom. Then after reaching up till here, the next thing would be in this problem to find the moment of inertia of this complete section, that is after the location of y bar. The next step would be to find the moment of inertia, and for that I'll divide this figure into three simple areas, that is area of this first rectangle, here we have second rectangle, and even the third rectangle. This is one of the methods. Another method you could have been used here is we can take the outer rectangle and from that subtract the moment of inertia of these two smaller rectangles. That would also give us the same value of moment of inertia. So whichever is convenient for us, we can move further into the problem by using that method. So here I am taking this as rectangle 1 and I'll say that since the mi moment of inertia about na, that is neutral axis, it is given by Ixx is equal to Ixx1 plus Ixx2 plus Ixx3. Keeping this as the first equation, then Ixx1 is the moment of inertia for rectangle 1 about the neutral axis, and therefore Ixx1 would be I1 plus area 1 into h1 square. This is by using parallel axis theorem. And now what is h1 here is, since the neutral axis for the complete I section passes through 100 mm from bottom and the x-axis of rectangle 1 is at distance half of 25, that is it is 12.5 mm from bottom and our references are from bottom. So the distance between the neutral axis and the x-axis for rectangle 1 would be denoted as distance h1. So here I would be writing the formula. First of all, I1 is the moment of inertia for rectangle 1 about its own x-axis and the formula is bd cube by 12 plus area 1 which is b into d, and h1 is y bar which is 100 minus half of 25 the whole square. Next, putting the values of b and d. Here the rectangle is having b value as 350, d is 25. Then 350 into 25 b into d. So here I would be getting the value of Ixx1 and it comes out to be 67.45 into 10 raised to 6 mm raised to 4. Now since here this I section being a symmetric section, whatever the value we are getting for Ixx1, same would be the value for Ixx3 because the top flange and the bottom flange are having the same dimensions. So like I had explained about distance h1, similarly distance h3 is also same, that is between the neutral axis and x-axis for rectangle 3. So I can say here that Ixx1 is equal to Ixx3. Similarly, I'll find Ixx2 would be I2 plus area 2 into h2 square, that is by parallel axis theorem. Now here something interesting I have to show you all, that this h2 distance would be 0 because the x-axis, that is the neutral axis for the complete eye section, and x-axis for rectangle 2 are at same distance, which is 100 mm from bottom. So distance h2 becomes 0, that is the neutral axis and x-axis for rectangle 2 are at the same level. So I can directly use the formula, that is h2 would be 0, and here we are going to only have bd cube by 12 plus 0, since the distance h2 is 0. B and D for rectangle 2. B is the width at the neutral axis, which is the width of the web, and that is given as 12.5 mm. So 12.5 into 150 cube, that is B into D cube, divided by 12. So Ixx2 value comes out to be 3.52 into 10 raised to 6. Now once we know Ixx1, Ixx2 and Ixx3, we can put them in equation 1 to get the total Ixx. So therefore, put all values in equation first. So in equation first we have Ixx, that is equal to Ixx1 67.45, and here it is having 10 raised to 6. I'll take it as common, plus Ixx2, which is 3.52, again 10 raised to 6 would be taken common, and Ixx3 is same as Ixx1. So the final answer is, after adding up all the values, 138.42 into 10 raised to 6 mm raised to 4. Now, after reaching up till this stage, that is finding the moment of inertia, the next step would be, as the question is we have to draw the shear stress distribution diagram for this eye section about its depth. So here I would be defining the layers over which we are going to calculate the shear stress over the depth. So this would be the first layer at the top, denoted by 1 1. Similarly at the bottom also I denote it by 1 1. Next, after covering a depth of 25 mm, there is another layer at second, layer 2 2. At this same height of 25 there is one more layer 3 3, which is having the width equal to 12.5 mm. Then similarly this 3 I'll even denote here that this is also 3 because of the symmetric section. The notations I'm keeping it as same to avoid any kind of confusion. Then there would be a layer at the neutral axis. Now I'll start the calculation of shear stresses, and remember, whenever you are calculating for shear stresses, the shear stress at the top and at the bottom for a rectangular section would be 0. For that you all can refer my video in which I had explained the derivation of shear stress for a rectangular section. Now, after naming all these layers, I'll go for the calculation of shear stresses. And the first thing here would be shear stress at layer 1, that is at top and bottom, are 0. That is for a rectangular section. Next, the tau or shear stress at section 2 can be found out by using the formula, which is a general formula of shear stress, Fa y bar upon Ib. Keeping this as equation second. Now, layer second is at the width 350 mm, means I would be taking this upper rectangle for the calculation of stress at layer second. So I'll draw the diagram separately. Here is the neutral layer or the neutral axis. The width is 350 mm for the rectangle or the flange, we can say. Depth is 25 mm. Here is the x-axis for this rectangle, and at the top the layer is 1, section 1, at the bottom it is section 2. So this is the area which I had taken in order to calculate the stress at section 2. Now the distance between the x-axis for this rectangle 1 and the neutral axis, here it is denoted as distance y bar, and when I look into the formula, F value is given into the problem, that is 200 into 10 raised to 3 Newton. Then area 1, here area is for this flange, so area would be similar to the previous area which we had calculated. It was 350 into 25, and the value is 8750 mm square. After getting the value of area, next is y bar. Y bar is the distance between the neutral axis and x axis for this section. So this y bar distance is, since the distance of the neutral axis from the top is 100 mm, so from this 100, if I subtract half of 25, that is going to give me y bar. So therefore y bar would be 100 minus half of 25, it is 87.5 mm. Then in the shear stress formula, always remember that moment of inertia is not for this area, but it is for the complete section. Like we have calculated this Ixx, that is nothing but the I which we are going to use in the calculation of shear stress. This is an important point which we have to remember. No moment of inertia calculation for the individual section while calculating shear stresses. We have to take the moment of inertia for the complete section. So that is known to us, and B is the width at the layer over which we want to calculate the shear stress, and here the width of layer 2 is 350 mm. So I'll say that B is 350 mm. So therefore, putting all values in equation second, and when I put all the values, tau at section 2 is equal to F, which is 200 into 10 raised to 3, area is 8750 mm square, y bar is 87.5 mm, I for the complete section is 138.42 into 10 raised to 6, and the width of the section is 350 millimeters. So from this I am going to get the answer of tau at section 2, and it comes out to be 9.87 Newton per mm square. So this is the value of shear stress at the second layer of width 350 mm. Next I would be calculating the shear stress at this third layer, and when I see this layer 3, it is at the same depth as layer 2, and here the width suddenly changes from 350 mm, it becomes 12.5 mm. So whenever we see in case of shear stress, the relation of shear stress and width, they are inversely proportional. So whenever width decreases suddenly, shear stress should increase suddenly. Like I can say that even in this formula we can see that tau is inversely proportional to B. So when we decrease B, tau is going to increase suddenly. So this layer 2 for the layer 3, I'll say that I am using the relation that since tau at layer 3 upon tau at layer 2 is equal to, when we take layer 3, its width should be taken into the denominator, and the width is 12.5 mm. Similarly for layer 2, the width was 350 mm. So therefore tau 33 would be tau 22 into 350 divided by 12.5. So the answer of tau 3, it is 49.33 Newton per mm square. Now once I get the value of tau 33, the only thing left here is tau at the neutral axis, because this being a symmetric section, whatever stresses we are getting up to layer 3, that would be same for the bottom portion as well. So now the only thing remains is stress about the neutral axis. For that I can take the area above the neutral axis or below the neutral axis, because the areas are same, they are going to give us the same value. So I am selecting this region at the top, I am just shading it. So this area would be used, this complete area, that is this much portion of the web and the flange, for the calculation of tau at the neutral axis. So therefore shear stress at the neutral axis is given by, the formula is F into, here it will be A1 Y1 plus A2 Y2 upon IB. I can say this is Y1 bar, this is Y2 bar, and that will be equation 3rd. Now I'll draw the area separately so that we can understand how to calculate the value of shear stress for this section at the neutral axis. This would be area first, and here we have area second. Width is 350 mm for the flange, and this is 25 mm thickness of the flange. Next, here at the neutral axis, this is the width of the web, 12.5 mm, and this height is, since here this is 150, the depth of the web, total depth, so this is half of 150, it means it is 75 mm. So I'll just go on putting the values here. F is 200 into 10 raised to 3. Area 1 is 350 into 25. Then Y1 bar is the distance from the neutral axis to the x-axis of rectangle 1. This height is Y1 bar, and it will be, since the total Y bar from the top to the neutral axis we had calculated initially, this was 100 mm. So it is 100 minus half of 25, that is 12.5 mm. 100 minus half of 25, then plus area 2. Area 2 is 12.5 into 75, and Y2 bar is the distance between the x-axis for this rectangle 2 and the neutral axis. So it can be clearly seen that this distance is Y2 bar, which is half of 75. Dividing completely by I, which is 138.42 into 10 raised to 6, and B is the width at the neutral axis, which is 12.5 mm. So from this I am going to get the answer of tau at the neutral axis, and it comes out to be 433.44 Newton per mm square. Then after getting all the values of shear stresses, now I am going to plot the shear stress distribution diagram for this symmetrical I section over the depth of the section. For that I am just going to project these horizontal lines to the right. First draw a vertical line Then tau at top and bottom, they are 0. We have seen it. Then tau at section 2, it came out to be 9.87 Newton per mm square. And remember that the variation of shear stress over the depth is parabolic. And how it is parabolic, for that you all can refer my video in which I had explained the derivation of shear stress. So here the variation is parabolic and it is having the value 9.87 Newton per mm square. Similarly, the same value would be there at bottom because this being a symmetric section. Then as we see here, from layer second to layer third, the width decreases suddenly. So shear stress increases suddenly at layer third and having the value as 49.33 Newton per mm square. Then at the neutral axis, the value is highest, which is 433.44. So this is the shear stress distribution diagram. For the given symmetric eye section, we have completed the problem, and just when I had completed the problem, if you all find my videos useful and helpful, please try to like, comment, share and subscribe this video amongst your family and friends. Thanks a lot.